All right. So this will be the last video in like the first kind of module or a week or whatnot. Not that we're on like a super strict schedule or anything, but it's going to be one really important application of linear algebra, which is solving systems of equations. And this will actually lead into a whole bunch of things regarding just an abstraction to ax equals b, which I'll explain what that is later. That'll introduce us to a whole bunch of other things. So to start, let's just throw a system of equations up here. Let's make it a three-dimensional one so that it's decently complicated. Let's make it x plus 3y plus 4z equals 2. And as you can see, this is going to get ugly real fast. X plus 4y plus 5z equals 1. X plus y plus 3z equals 4. And I did this beforehand to make sure all the numbers worked out. But you might ask, like, why do we need a new way to solve this? Like, maybe you already know a way to solve this, even though it might take a while. You like solve for x and do replacement and then replacement again, and then you'll eventually find your answer. Well, the answer is when you do it using linear algebra, as you'll see, there's like a method to it. There's kind of a pattern, and as a result, it's really easy for computers to use the linear algebra method. So all of this work that we're going to end up doing in order to use linear algebra to solve this equation, it makes a really fast and easy way for computers to do systems of equations. And for the most part, anytime you're doing systems of equations of like 1,000 variables and you need a computer to do it, it's going to use this method. So that's kind of why this is so important. So let's first talk about how we can use matrices as an abstraction. In the very first video, we talked about how matrices are basically just some arbitrary collection of vectors, where vectors are just some arbitrary collection of numbers. So it really can represent anything, but here we're going to specifically use a matrix to represent this system of equations. So a really simple way to do that, and at first it might just seem like random, but we'll see how it can actually be helpful, is that we just take the coefficients here and the numbers, and we just make a big old matrix. So this being the coefficient of the x term, the y term, and the z term, and then we have a 2 here. And it might seem kind of random and arbitrary the way I'm doing this, but hopefully later on it'll seem less arbitrary when we start talking about the geometric interpretation of some matrices. I'm going to put a little bar here just to separate as kind of this equal sign from one side from the other. It doesn't really have any mathematical significance. So we've just made this a matrix, and it's just some arbitrary collection of numbers that happens to represent all of the data from our system of equations. Now let's think about what we ultimately want. What we ultimately want is we want to have the value for x, we want to have the value for y, and we want to have the value for z. And let's think about what this looks like if we were to convert this into a matrix using kind of our rule of thumb. Well, we know that the x coefficient here is 1, the y coefficient here is 0 because there's no y, and the z coefficient is 0. In this one, we have no x, so the coefficient is 0, but we have a y and no z. You see, I'm just using the same rules we used over here to make this matrix, but we're doing it on this one. And then over here, we have some random variables. Let's call them a, b, and c. Those are ultimately going to be our answers. So if we can get our matrix to look like this, then we know that our x is going to be whatever a is, our b is going to, or our y is going to be whatever b is, and our z is going to be whatever c is. So the question is, how do we get from here to here? That is the essential question. And to do that, we're going to use 3 rules, and you can see them right here. These are our 3 rules. But let's explain where they come from, because I think a lot of times in class, they just kind of give you these 3 rules. But let's talk about where they come from. So the first rule is scalar multiplication. What that means is that we're allowed to multiply any row by a number. Now let's think about why that's the case. Well, if we go back up here to the algebra, which we're all familiar with, we all know we can multiply this by a value, as long as it's the same value on both sides, and it's still an algebraically true statement. Likewise, we can multiply through this entire row right here by the number 3. This would be 3, this would be 9, this would be 12, this would be 6, and it'd still be algebraically correct. The numbers would be different, but we would still have the same system of equations. So that is why this first rule is allowed. Let's go on to the second rule, swaps. What this means is that we can swap any row for another one. This is also easy to make sense of because if you look at our original equations, if I wrote this equation here and this equation here, it wouldn't change the ultimate answer. I've just written the equations in a different order. Likewise, in this matrix, I'm allowed to switch rows and we'll still have the same system of equations that we're working with. So that second row makes sense. Third row is a little bit harder, but it's not if you remember how to solve systems of equations by like adding, you like stack the equations on top of each other and add them. So the third equation is addition. It means that I can add two rows together essentially, or add one row to another to get another row. And the reason this works is, say for example, I add this to this, and I add this here. By the law of algebra, if I add the same thing on both sides, then we're all good. So have we added the same thing on both sides? Well, yes, because on this side we added x plus y plus 3z, and on this side we added 4. But because of this equal sign, by definition, these two things are the same. So therefore, we can add in this sort of way where we add one side to one thing and add another side to another thing. An example of this on our matrix equivalent would be just like this green is being added here and this green is being added here. We can add these values to this row and this value to this row. What that would yield is the first row stays unchanged. The second row has had some addition done to it, and you can check how I'm getting these numbers. And then we also leave the third row unchanged. And so that's an example of the third rule right here and an explanation for why we are allowed to do it. So hopefully these three rules make sense. I think that's probably the most important part of this video is why these three rules work, because in class there's like probably a 70% chance that we're just going to be given these rules. So moving on, let's see how we can use these three rules to manipulate this matrix into one that we like, which is this second one. Because if we get this second one, then we're golden. So I'm just kind of speed through this because this is definitely something we're going to learn in class, and it's not really important. I just kind of want you to get the idea. So for example, I'm going to subtract the first row from the second row. And again, if you don't follow this, not really that important. Subtract the first row from the second row. I'm going to subtract the first row from the third row. I'm going to add twice the second row to the third row. I'm basically just following these rules. And as we get more practice, it'll be more natural. And you might start to see how I'm slowly kind of building this over here. And I'm going to give a name to this right here. This is reduced row echelon form. So this is my goal. I want to get this to reduced row echelon form. So I'm going to keep going here. Hopefully I haven't made a mistake. Add twice the second row to the third row. That gives me this and this. I'm going to subtract the third row from the second row now. So you see I'm getting pretty close. I'm going to subtract 3 times the second row from the first row. Maybe that. I mean, again, I might have made an algebraic mistake in here, but it really doesn't matter. I'm going to subtract 4 times the last row from the first row. And I think that does it. Through a bunch of these rules, just applying these three rules, I've gotten to reduced row echelon form. Now we can take this back out of matrix form to regular form, and we have, following the rules of how we set our coefficients up, etc., we have this. And again, you could probably take these numbers and go back and check in our original equation whether they actually work. Again, I might have made a mistake. Doesn't really matter. But you can see how we can use matrices to solve these sorts of equations. And this is exactly what a computer does, and this is exactly what you'll do next semester. So let's move on to how this kind of shows some intuition on how we can find linear independence. So let's think about what a system of equations really is. So systems of equations, let's say we're in 3 dimensions, right? So there's my z-axis, x-axis, y-axis. A system of equations is basically saying, here's a line, and here's a line. And it's basically saying, like, where do they intersect? And sometimes they will all intersect at one point. Sometimes, like, 2 of the lines are in the same direction and things like that. So by solving a system of equations, whether or not it gives us this nice reduced row echelon form is actually telling us whether 2 of the arrows are pointing in the same direction. Because, for example, let's go to a two-dimensional case to make it even simpler. Let's have the line y equals 2x. Uh, yeah. And then let's also have the line 2y equals 4x, right? If you recall, if you try to solve this systems of equations, you're going to get a weird solution. Why? Well, these lines are the same. They basically stack on top of each other. So where they intersect has infinite solutions. If I use the substitution y equals 2x here, I'm going to get 4x equals 4x. And I'm like stuck. I can't really go any further. This is just a true statement no matter what x I put in. So, as we'll probably cover in class as well, to check for linear independence, what you do is say you have three vectors. I'm going to make these up. 1, 2, 3, 4, 5, 6, 5, 7, 9. Notice how this last vector is actually the first two vectors added together. That means that this vector is dependent on the other vector. It lies in the same plane as these two vectors, as the span of these two vectors. So if we make a matrix out of these three vectors, matrix where these are the columns, and we try to use this the three rules to reduce this down, I'm going to take a pause in the video and do that real quick, and we'll see what it gives us. All right, so I've done a couple of these rules, and you'll notice that our second two rows are looking kind of suspicious. For example, if I multiply the second row by 2, I get exactly the third row. And then if I add the second row to the third row, I get a row of zeros. And this is interesting because if I have a row of zeros, I can never get to the reduced row echelon form that we aim for. So if we can put the matrix where the columns are the vectors, and we have a matrix like that, if we can take it to reduced row echelon form, and the abbreviation is RREF, then the vectors right here are linearly independent, right? We can think of it as a system of equations where all of the lines kind of point in different directions and intersect. However, if you cannot go to reduced row echelon form, like right here, where you end up with a row of zeros, then they're going to be linearly dependent, or LD, and that means that one vector lies in the same vector space as the span of the others. Hopefully that makes a little bit of sense. It's okay if it doesn't totally, but you can kind of see this relation between systems of equations and linear independence. Let's finish up with what did I mean by AX equals B? Well, there's actually a way to write this as a complete matrix vector operation where you have a matrix A with all of our coefficients. You have a vector X, that's this X right here. And then that gives you some vector B that has numbers in it, like A, B, C. And we'll come back to this because in order to fully understand this, we need to understand what it means to multiply a matrix by a vector. And that is a very big topic all in itself. And it has to do with a lot of geometry. So that'll be really interesting, and we'll talk about that next week.